In the last video, we talked about these things called capacitors. And to be honest, they're very important. You'll find a capacitor in almost any major electronic device that you carry. Your computer has capacitors. Your phone has capacitors. Cameras have capacitors. And the main purpose of a capacitor is they're a part of a circuit that is able to store energy for a little while. And the way they store energy is by mounting charges on two opposite plates. So for example, as I told you before, a capacitor will often have a positive plate or a positive side and a negative side, right? And of course, these actually have an area, right? So there's some width to them, okay? And you're going to have electric field lines then that point from one side to the other, okay? But how do we know how big that electric field is? In the last problem, they just told us how big the electric field is. Is there any way to actually calculate it? And the truth of the matter is yes, and it's very simple. So the electric field inside of a capacitor is just equal to the charge on the capacitor plates. So there's going to be a charge, negative charge here of negative Q, and a positive charge here of positive Q, right? And so it's not 2Q, it's just whatever the charge is on each plate, Q absolute value goes on top, okay? These charges will have to be the same. There's reasons for that in a circuit, but we won't get into that right now. But just know these charges are going to be the same. And so on the bottom of this equation, you're going to have epsilon naught over the area of the plates, okay? So the electric field of a capacitor goes up when the charge goes up and goes up when the area goes down. Okay, the smaller, if you can fit more charge on a smaller area, you have a bigger electric field inside there, which makes sense because those electric field lines are going to get squeezed together, and we said when electric field lines are closer together, the electric field goes up. Cool, right? So a reminder, this epsilon naught, the permittivity of a vacuum, is 8.85 times 10 to the minus 12. All right, and with that said, we'll do a simple problem involving something that you wouldn't think is a capacitor, but it really is kind of a capacitor, and that is a thundercloud. All right, so let me read this question. Thunderclouds are essentially capacitors with one plate being the cloud and the other being the ground beneath it, right? So you basically have little cloud, right? So that's one side of the capacitor, and then you have the ground, right? And so imagine a circular thundercloud. So this is circular base with a certain radius, and that radius is 120 meters. What charge would it take to exceed the dielectric breakdown of air, which is the electric field that is strong enough for electrons to actually make the jump from here to the ground? Okay, so for example, let's suppose that because these clouds are all mixing and mashing together up in the sky, there's some friction there, and like you're pulling some net charges on some clouds, and positive charges on some clouds, negative charges on other clouds, and so you have this cloud has a net negative charge, let's say, right? And these electrons don't like to be on this cloud, right? They're like, I'm too close to too many other electrons. Doesn't feel good. Starting to panic, right? So these electrons say, I really, really, really badly want to jump to the ground. Lightning. And so what do? They say, well, here's the thing. That's quite a leap of faith. That's quite a big jump right there. I'm only going to do it if there's so many electrons that I really, really can't stand it anymore and need to make that jump. Okay? That's the dielectric breakdown. So the dielectric breakdown is how big does this electric field here have to be so that these will actually jump from here to here. All right. So let's suppose that electric field necessary for them to jump is 3 times 10 to the 8 newtons per coulomb. Okay? What charge would you need on here? What charge would you need on this cloud in order to get that strong of an electric field to create that effect? All right, well, let's look at it. We know that the electric field of a capacitor, because we're modeling this as a capacitor, is the charge on each plate over epsilon 0 times A. This means that charge is just going to be equal to the electric field times epsilon 0, the permittivity of space, times the area. But the area is a circle, right? So we're saying the bottom of the capacitor is like this. That's the bottom circle. Here's the top circle. And it's got a radius of 120. We know that a circle has an area of pi r squared. So this is just going to be pi r squared. OK. And I'm going to erase this really quick. And since I'm running out of space, I'm going to write it over here. E is, we found out, 3 times 10 to the 8 newtons per coulomb. Epsilon 0 is 8.85 times 10 to the minus 12. And pi is pi. And R is 120 meters. So we do 120 squared. And what do we get? I get that the charge required for the electrons to jump down and have a dielectric breakdown of air and you see lightning is going to be 120 coulombs. And that doesn't seem like a lot of charge, but remember, that's a lot of charge. All right, 1 coulomb is enough so that 3 kilometers away, 2 people holding 1 coulomb will feel a force of attraction as strong as gravity. So that's pretty powerful. That's how much charge gets mixed and mashed in clouds, and that's why we end up seeing a real cool lightning bolt come down. All right, and now you know something to tell your friends and family over dinner.